Okay, good afternoon, everyone. Welcome. Thanks for joining. And so we have a lot to talk about today. Last three classes, we've been talking with you about plane waves, about different kinds of plane waves and the forms that they can exist in different media. We talked about plane waves in dielectrics, metals, negative index materials, hyperbolic media. We talked about what happens to plane waves at boundaries between different media and how they experience reflection and refraction. And lastly, we talked about how we can compose different combinations made of a superposition of various plane waves and how it leads to cylindrical beams, Bessel beams, Gaussian beams, and also to the effect of super oscillations. And what if, let's say, we have some electromagnetic energy in place A and we want to transfer that electromagnetic energy to place B. And we have to launch to excite some radiation, and that radiation will deliver energy from point A to point B. And a plane wave, exactly the plane wave that we discussed last three classes that we've been discussing, is such an elementary carrier of electromagnetic radiation and electromagnetic energy. So we need to create a plane wave, and that plane wave will carry energy. But the problem with plane waves is that they are infinite in space, infinite in the propagation direction, infinite in the transverse direction, and they carry infinite energy. Plane waves are non-existent. And we need to be able to create some other form of electromagnetic excitation that is localized in space, localized to some region of space, and that can carry that energy, or maybe that signal that is encoded in the amplitude and phase of the radiation from point A to point B in a canal of space with a certain transverse dimension. And for example, the Bessel beams that we discovered the last time, they can do this in principle. They can achieve this goal because they are localized, they are focused beams. And in principle, one could expect that one could use the Bessel beam to transfer energy or information from point A to point B. But the problem with Bessel beams is that they also carry infinite amounts of energy. Their intensity is infinite. If you were to calculate the Poynting vector of a Bessel beam and integrate the entire intensity of the Bessel beam across the xy plane, and let's say the propagation is in the z direction, you'll see that the intensity, the total intensity of a Bessel beam is infinite. That's because it is composed of a set of plane waves that all have the same z components of the wave vector. Okay. And this is essentially why Bessel beams are non-diffracting. The infinite intensity, the infinite energy flux carried by a Bessel beam is what allows any kind of Bessel beam to preserve its shape upon propagation. But there is another kind of beam that we also studied last time, the Gaussian beam. And Gaussian beam is finite; it has a finite energy, but this finite energy comes at a cost. Gaussian beams diffract. They diffract upon propagation, and we clearly saw this the last time. They get narrow when they approach the focal plane, and then they start to diverge. This is a fundamental property of a Gaussian beam. So we need to find something else to be able to guide electromagnetic energy and information in a certain narrow region of space. And this is exactly what we need waveguides for. So a waveguide, generally speaking, is any kind of multi-layer structure that involves metals, dielectrics, mirrors, periodic structures, resonant materials, and so on and so forth. Just any material, any boundaries between different materials. For example, boundaries between dielectric and metal, boundaries between two different metals, and so on and so forth. And has at least one direction with continuous translational symmetry. And these are just two prototypical examples of waveguide. You have a waveguide with rectangular cross-section, and another sketch shows waveguides with circular cross-section. And in such a system, the boundaries between different materials, the boundary between the environment, in this case it's air, and the dielectric material, the core of the waveguide, the boundary is what allows us to localize the energy in that core of the waveguide and to propagate it, to carry it from point A to point B with preserving its shape without scattering to the environment, and the energy, the total intensity of that thing, of that field that exists in the waveguide is finite. And so the mathematics here is the following. If we have a waveguide mode, if we have a waveguide with at least one dimension in which the system has a continuous translation invariance, then the fields, electric fields of this waveguide mode can be written in the following way. So we have certain distribution in the YZ plane in which the system has some non-trivial distribution of refractive indices. And then we have this phase factor, which describes how the waveguide mode propagates along the waveguide axis. In this case, the waveguide axis is directed along the x, and so this thing is what characterizes the propagation of the waveguide mode. This is the propagation constant beta, and this is one of the key characteristics that describe any waveguide and any waveguide's modes of any waveguiding structure. Okay? So usually in most cases we'll be assuming that the environment around the waveguide is filled with a dielectric, with an isotropic lossless dielectric material with certain refractive index n, and that then k naught is the wave number in that surrounding media. And then we can do an important thing. We can introduce the concept of the dispersion diagram. So now we can write the fields, the asymptotic behavior of the fields in the environment, assuming that the system has, let's say it's a planar system. In other words, our waveguide is certain stack of films, 1, 2, 3, etc., n films. And this is our coordinate system, x, y, z. And the system is invariant in x and y directions. And let's say we're interested in propagation along the x-axis. So the fields, the behavior of the fields along the z-axis outside the waveguide will be characterized by these two asymptotics, by these two asymptotes, which in the limits of infinite z behave as plane waves with certain kz, which we'll talk about later. And now we can split the dispersion diagram, all the set of points b, beta, and omega, into two parts: into the radiating region, where beta is smaller than kappa k naught, and the bound region, where beta is larger than k naught. So this is the radiating region, which is also called above the light line, or within the light line, or within the light cone. Terminology differs, but you get the idea. And this is the bound region, which is also referred to as being below the light line. This is the light line, which characterizes the dispersion of our plane waves in the environment. And what you have below the light line will be of particular interest for us today, because this is where waveguide modes will typically exist, with certain exceptions. Okay, so the radiating region, the solutions that we have in this radiating region are usual plane waves that are incident on our multi-layer structure. On top, getting reflected, getting transmitted, getting scattered generally. And asymptotically, they behave just as plane waves with certain oscillatory behavior. And they are not localized. They behave just as plane waves or standing waves with respect to the z-axis. And they carry energy along the z-axis. They carry energy in, they carry the energy out, away from the system. And these are just plane wave solutions that experience scattering. And the important thing here that I want you to emphasize, that I want to stress, is that if you go back to this dispersion diagram, then in the radiating region, for any, if we pick any value of beta, there will be a continuous spectrum of solutions for that particular beta. You have a solution for this frequency, for this frequency, for this frequency, and so on and so forth. And there will be a continuous set of solutions for every fixed beta above the light line in the radiating region. These are propagation constant is the characteristic of the waveguide mode that characterizes the phase velocity. So the waveguide mode as a whole, it can have a very complicated distribution in the YZ plane. It can be focused, usually it is focused in the waveguide core, and then it decays exponentially when we go away from the waveguide. It depends on the material and on the shape and on the frequency, on everything, basically. We'll talk about it later. For now, you need to understand that the propagation constant is a certain number, usually a complex number, that describes how this thing as a whole propagates in this direction. So as it propagates along the z-axis, the field will behave as e to the power I beta, this is x. So this is like a plane wave, except that the plane wave is, well, it's a plane of everywhere. But this thing has a very complicated distribution. It may have a very complicated distribution if you look like this in the transverse plane. But in this direction, it behaves as a plane wave with this phase accumulation factor. And this is also just the frequency dependence, which we always assume. Okay? Right, so that's the radiating region where our solutions are just plane waves getting scattered by the system. No localization, no waveguides, and that's just reflection and refraction in different terms. But the below the light line region is where interesting things happen. So now our beta exceeds k0. And if we find, if we try to understand what it means for those plane waves that exist outside the system, then we'll see that they become evanescent. So the field outside the waveguide must be evanescent because the plane waves outside, they satisfy the dispersion relation, right? Beta squared plus az squared equals omega over c squared. And if beta is larger than k0, obviously kz has to be imaginary. And we will be particularly interested in the case when this imaginary quantity is such that the field is exponentially attenuating, decaying exponentially away from the waveguide. And this gives us exactly what we want. This gives us a waveguide mode. Certain solution that has certain field distribution inside our multi-layer structure, waveguides, anything, it's absolutely anything. But outside, it behaves as a pair of evanescent waves. One wave is attenuating in this direction, another wave is attenuating in minus z direction. Okay? And this is expressed by these asymptotics. So if kappa is larger than 0, if it is chosen to be larger than 0, if it can be larger than 0, that depends on the particular system, then our fields will satisfy this dependence at infinitely large z. And this will give us a waveguide mode that is exponentially localized near the structure and that propagates with a propagation constant beta in this direction. This is essentially the waveguide mode. And this waveguide mode, it carries energy only in the longitudinal direction, only along the waveguides, but not in the transverse direction. It does not carry any energy along the z-axis, only in the propagation direction, along the x. And another important difference with the radiating region is that now, for any given beta, you have only discrete spectrum of solutions, discrete spectrum of bound modes. And bound is a synonym for localized. For every beta, you're going to see only a discrete spectrum of modes. There may be infinitely many of them, that's a different question, but it is guaranteed to be only discrete. It cannot be a continuous spectrum like in the case of radiating region. So it is also useful to classify possible guided solutions of any waveguides into proper and improper modes. So proper modes, a proper mode is any mode, any solution any stationary monochromatic solution of the system that decays exponentially away from the waveguide. So it decays in the positive z direction and decays exponentially in the minus z direction. Doesn't matter what is the nature of this decay. If it decays, then it is called the proper mode. And the modes that we will be interested in the next few classes are always proper modes. We are interested in proper modes because they guarantee exponential localization of the energy. And they behave just like that with longitudinal energy transfer and exponential localization. This is the basic characteristic of proper mode. And improper mode is, of course, the obvious, the opposite, sorry. Improper solutions are characterized by exponential divergence along the z-axis. So very similar characteristic, but now we flip plus and minus here. See? Which yields exponentially divergent solution. And these solutions are unphysical. They do satisfy Maxwell's equations mathematically. Well, they are valid solutions in the mathematical sense. Maxwell's equations are satisfied, but these solutions are unphysical because the field magnitude, the intensity, it blows up as you go to infinity, and there isn't any physical finite current distribution that can excite such a mode. And at infinity, you usually assume that there are no fields at infinity because, well, otherwise the energy, the intensity of this solution is just infinite. And it doesn't make any sense when the field explodes as you go infinitely far away from the structure. So these modes, they also called anti-waveguide modes. Sometimes you're going to see that in the literature, and they're unphysical. We're going to discard these modes. They will appear as solutions of Maxwell's equations sometimes, but we are not interested in the solutions, okay? Leaky modes. This is something interesting, something different. There's a lot of confusion in the literature among people about when it comes to leaky modes. So a leaky mode is a solution for a waveguide system, for any system that has translational symmetry, all these slabs, films, whiskers, cylinders, and so on and so forth. Anything with one translation invariant dimension. These are the modes of such systems that radiate energy away from the waveguide. So remember all these proper and improper modes that we studied so far, that we mentioned. They were characterized by strictly longitudinal energy transfer. The energy propagates just from point A to point B along the waveguide. It can be localized exponentially, it can be exponentially divergent, but the energy transfer is longitudinal. Here, there is a transverse energy transfer. Transfers energy transport away from the waveguide. So to understand how leaky modes behave and how they come into play, let us again write the asymptotic behavior of the field at infinity. This is, well, the usual planar behavior with different signs depending on how we choose the wave vectors. So outside the waveguide, here and here in the top and in the bottom, this propagation constant and kz, they satisfy the usual dispersion relation, where k0 is the wave number in the environment, beta is the propagation, and kz is the z components of the wave vector. And because, now let's think, because these leaky modes, they radiate energy from the waveguide, they must lose energy upon propagation, because the energy must be conserved. And if they radiate, they should attenuate in the propagation direction, which means that the propagation constant should be complex valued, because that's the only way to introduce attenuation, longitudinal attenuation exponentially. So mathematically, so this thing, again, this is a generic sketch of certain generic waveguide that supports a leaky mode, and this shows you how the field behaves in the longitudinal direction. It decays exponentially because energy is radiated. It's constantly leaking away from the waveguide. Since hence the term leaky, because the energy is leaked from the waveguide. And this energy leakage is expressed by a complex propagation constant, where the positive imaginary part expresses energy attenuation as the mode propagates. But because this is complex and this is real, Remember, we're assuming that the surrounding is a lossless transparent dielectric. This must be complex too. So Kz must be complex too. Okay, so this is quite interesting. Now the mod might have very complicated non-homogeneous behavior in the x and in the z direction. Let's explore that. So let's just take the same dispersion relation for the wave number, wave vector in the environment and rewrite it in terms of the real and imaginary parts. This is alternative absolutely equivalent to this. This is same exact stuff. You can verify it on your own. Just written explicitly in terms of the real and the imaginary parts of K, where K is the two-component vector. And now if we recall that beta and Kz are complex, we can inspect particular cases. So without loss of generality, we can assume that beta prime is positive. The waveguide mode propagates in the positive direction of the x-axis, so it must decay in the positive direction. Therefore, we can, without loss of generality, say that beta prime is positive. But then we have to remember that the energy is leaking in both directions in this axis, in this direction and in this direction. And in order to account for this energy transfer, Kz prime must also be positive. This is just compatible with the way we expressed the field previously. This is compatible with energy transfer in this direction and in this direction if real part of Kz is positive. And this, along with this, leaves us only two alternatives. Either I'm sorry, this is beta double prime, because this is the decay. The mode decays along x, and the decay is expressed by the imaginary part of beta. So this is beta double prime is positive. So this leaves us two alternatives. Either real part of beta is positive, but the imaginary part of Kz is negative, or vice versa. And let's explore what these two cases really mean. So the first case, the first option, where beta prime is positive and Kz double prime is negative, this is so-called forward leaky mode. In the forward leaky mode, the energy is radiated in a forward directed cone, in the forward direction, away from the waveguides and also in the positive x direction, and the mode attenuates in the same direction. Okay? And the same radiation happens here. But what's unusual about that is that this leaky mode, forward leaky mode, is improper. The field, because of that, the field diverges exponentially along the z-axis. And this is still a physical mode. This divergence is physical. So how can we understand this seemingly unphysical behavior of a leaky mode with exponential divergence along the z-axis? Well, we need to look precisely at this energy radiation process, at this leakage process. So because the energy is radiated forward, let's freeze time and take a snapshot of the field. And let's see, let's take a vertical cut of this figure and look at the magnitude of the electric fields at certain x naught. And we're gonna, let's say, record the magnitude of the electric field here, intensity of the field here, and intensity of the field here. So in the field here, it was radiated from this point of the waveguide, right? But the field here, intensity that we could see here, it was radiated here. This corresponds to an earlier moment of the wave. So here, the wave was more intense because it decays in this direction. Remember? So the intensity that you're gonna see here, it comes from the past of the leaky mode that propagates along the waveguide. And so as we go away from the waveguide in the vertical direction, we're gonna see more intense fields. And because of that radiation process, this exponential divergence is completely physical just because of causality. This is what a forward leaky mode looks like in simulations. So this is some sort of dielectric waveguide which is excited here at the entrance, and then the mode propagates, a guided mode. But you also see this cone of radiation, and this radiation is exactly, it originates from the excitation of a leaky mode. So you see that the energy goes along this, at this angle. And you don't quite see on this plot, in this simulation, you don't quite see this exponential divergence because you'd have to wait longer. You'd have to simulate the propagation of this mode on a longer scale. And then if you were to go up here, then you would see that the field starts to diverge as you go away from the waveguide. So this is just not, there's not enough space in this plot to visualize the exponential divergence. But this is an illustration of how a leaky mode can really appear in a realistic situation. But this is not the only type of leaky mode. Remember that there was another alternative with opposite signs of beta prime and kz double prime. And we can expect that alternative too. And this alternative corresponds to a backward leaky mode. So why backward? Well, because now beta double prime is still positive and energy propagates in that direction. But beta prime is negative. So the phase velocity in this wave is opposite to the energy velocity. This is a backward wave. This is the definition of a backward wave, where the phase velocity and energy velocity are contra-propagating. Like in a negative index material, this is a backward wave. And because the energy is now leaking not in this direction, not in a forward cone, but in a backward cone, there is no exponential divergence in the z direction, because the energy that you see here comes from here, but the energy that you see here comes from here, where the wave has decayed, because energy propagates this way. And so in a backward leaky mode, there is no exponential divergence. It is a proper mode, unlike forward leaky mode, which is improper. Now, one last thing that I want to stress about leaky mode is that there is a common misconception in the literature. You often see people say that leaky modes can only exist above the light line. Well, because they radiate energy, they must leak energy, and this process of leakage is only possible if beta prime, is less than kappa naught. Because this is the only situation in which a wave can radiate energy to the environment. This is not true. Leaky modes, because they have not real but complex valued propagation constant, they can easily exist below the light line. So the real part of propagation constant can easily exceed k naught, and this is still going to be a leaky mode. It will radiate to the environment without any troubles. Okay, that was it. That was a general intro into waveguides and waveguiding. And now we can switch to, now we can discover specific examples of waveguiding structure. And we're gonna look at two different strategies that enable waveguiding. Just up to that point, we mostly examined the cases where the environment is fields with a transparent dielectric with some refractive index. And we said that in order for a solution to describe a proper localized modes, we need to exist below the light line. Well, there is another way to achieve localization of wave, which is much simpler. That doesn't require any evanescent waves. We can simply stick two metallic planes together, take two perfect conductors, place them at a distance L from each other, and we can localize it, electromagnetic energy, in the space, in the region between these two parallel conduction plates, right? And our wave is gonna bounce back and forth and overall propagates in the x-axis And this is parallel plate waveguide, which you know probably from general physics. And this is, despite its simplicity, it's a very common and very useful structure that can illustrate a lot of physics common for all waveguides. And so we're going to begin with this. We're going to consider two perfect metallic plates at a distance L from each other. And solutions generally will split into two polarizations, into two polarization states: TE, transverse electric, and TM, transverse magnetic mode. So for TE modes, the electric field is strictly perpendicular to the propagation direction. So if the propagation direction is along the x, electric field must be strictly perpendicular to that, and it will be parallel to the y-axis. So we write the electric field in this way, plug that into Helmholtz equation, and we obtain this. Then, after some manipulation and after imposing boundary conditions, a tangential component of the electric field at the lower and upper mirror must be 0 because these plates are perfectly conducting. We obtain the electric field distribution of nth mod in the space between, in the region between the two parallel plates, and the dispersion. This is the key result. This is the frequency dispersion of transverse electric mode, where n is the index of the mode. So you see what happened? We assumed certain propagation constant beta, which can be any positive number, and for this beta we obtained a series of solutions that are labeled by the mode index n. And for every beta and for every polarization, we obtain a series of different curves. And we run this absolutely the same procedure for TM polarization, where magnetic field now is strictly perpendicular to the propagation direction. Plug that into the wave equation, obtain the field distribution, in this case the distribution of the magnetic field, and the frequency dispersion. Absolutely straightforward procedure. Okay? And we plot the dispersions. Let's look at them. So I'm sure that you recognize these dispersions. It describes frequency. No, let's say the other way. It's not frequency dependent propagation constant. It is the frequency that is dependent on the propagation constant, because dispersions of guided modes are usually plotted in these coordinates where we have propagation constant on the x-axis and frequency on the y-axis. And it shows a series of transverse electric and transverse magnetic modes. So what can we see from this plot? Each mode, each TE and TM mode starts from beta equals 0 at a certain point, at a certain frequency. And below that frequency, the propagation of that particular mode is not allowed in the waveguide. What's more interesting is that for TE polarization, there is a global cutoff, below which, in this region, TE polarization is not allowed at all for any index. 1, 2, 3, doesn't matter. You cannot propagate TE polarization once the frequency is below that limit. This is the global cutoff frequency. But TM mode, however, cannot propagate at any frequency. Transverse magnetic mode, transverse magnetic 0 mode, doesn't have any cutoff. It can propagate no matter how small the frequency is. So we can find these cutoff frequencies for each individual mode and polarization simply by assuming beta equals 0 and by plugging 0 in that equation. It's that simple. And we obtain series of cutoff frequencies for nth mode. But the 0 mode, TM0 mode, propagates without any cutoff. And this is a characteristic trait of the parallel plate waveguide and the TM0 mode of that waveguide in particular. So this is the field distribution of the few lowest TM and TE modes. TM modes in blue, they show the distribution, spatial distribution of the Y components of the magnetic field. So this is the Y component of the magnetic field, and this is the Y components of the magnetic field for TM1 mode. Okay, and green curves, they show the distribution of the Y components of the electric field. So for TE modes we have TM modes we have cosine-like distribution, And for TE modes, we have sign-like distribution because electric field must be 0 at the plates. And for TM mode, magnetic field doesn't have to be 0. It's still the tangential electric field component, which has to satisfy boundary conditions at the metallic surfaces. So TM mode is interesting. TM mode, it doesn't really have any interesting field distribution. It's constant. Magnetic field is constant across the vertical coordinate along the Z, and it's always perpendicular. And electric field is strictly vertical. Electric field is just like that. It starts at one of the plates and it terminates at the other plate of the waveguide. And this is why this mode is also called TEM mode, transverse electric magnetic, because it transverse magnetic and transverse electric at the same time. Both the magnetic and the electric fields of this mode are perpendicular to the propagation direction. But also, it should remind you a capacitor, because this is basically a capacitor. Two metallic plates, they aren't charged, but when a waveguide mode propagates in the region between these two metallic plates, it must induce a potential difference. This is going to be, so the electric field starts at plus, right? Or at minus? Yeah, at plus. So this is going to be positive potential. This is going to be negative potential. And then it's going to alternate because you have certain wavelength and the electric field will flip, and this is going to be plus, this is going to be minus. So this is such a spatially alternating capacitor. This mode is referred to as a capacitor mode. This TM mode, which doesn't have a cutoff, this is a capacitor mode. You just put two metallic planes together, you have a capacitor, and waveguide mode can propagate at any frequency without cutoff in this parallel plate waveguide. Sweet. Let's move on to a different geometry, to a cylindrical waveguide. So now we consider a cylindrical cavity of radius A, surrounded again by perfect electric conductor, of course, and translationally invariant along the x-axis. This is another type of waveguide. And we can, again, try to find the guided solutions of this structure. We can classify them into T and TM, as always. And if you remember the classification of vectorial basal beams, this is going to be useful because the vector structure of these guided modes, it repeats the vector structure of cylindrical basal beams. So where were we? Hollow cylinder waveguides. Yeah, a cylinder surrounded by perfect conductor, and we're looking. We want to find guided mode of this structure. Possible solutions split into two polarization states that are consistent with the vectorial basal beams. TM polarization means transverse magnetic, means magnetic field is strictly always perpendicular to the cylinder axis. So Hx is 0, and the only three non-trivial components in this case are the radial components of E, the x axial components of E, and the angular azimuthal components of H. TE polarization is analogous, means electric field is always perpendicular to the cylinder axis, and the only non-trivial components are the radial and axial component of H and the azimuthal components of E. So now math becomes quite cumbersome, so I can just walk you through this math very briefly, and I'm going to skip a lot of technical details. But long story short, for TM polarization, the axial components of electric field satisfy the basic equation. Basically, if you plug the entire field distribution into wave equation, you'll see that the Ex satisfies the basic equation, and therefore the general solution for Ex in cylindrical coordinates can be written as this. The radial part times the angular part. The radial part is a superposition of Bessel function and Neumann function, which are solutions of Bessel equations, and the angular part is this thing, which is just the angular exponent. And M will be referred to as the azimuthal index of the mode. But of these two functions, only Bessel function J is finite at the origin. Neumann function blows up at origin. So we cannot keep this. So the solution can be written just as this simple expression. And because this sum of plus I and minus I m phi is basically, because the system has it's identical in clockwise and counterclockwise directions, we can reduce this just to, we can keep just one, okay? And then we need to satisfy the boundary conditions. Again, boundary conditions are the same. It's that the tangential component of the electric field is 0 at the surface of the cylinder. It has to be 0. And now I'm going to skip a lot of math and give you the results, the characteristic equation and roots of this characteristic equation. This is the characteristic equation. It determines the propagation constant. So from this equation we find K rho, which is the radial component of the wave vector. You plug that here, and this gives you beta, the propagation constant. Now repeats exactly the same for TE polarization. Now it is the axial component of H that can be written as a product of Bessel Neumann functions and the angular exponents. We get rid of the Neumann function for the same exact reason. Then we impose the boundary conditions. Boundary conditions are the same. It's not complete analogy because magnetic field can be non-zero at the surface of the electric conductor, but the electric field cannot. So we express electric field through the magnetic field, require that it is 0 at the surface, and we obtain characteristic equation for TE modes. Note that there is a prime in this dispersion equation, which makes it different from the previous characteristic equation for TM modes. And this is basically the result. This is it. This is the dispersion relations for the perfect conductor circular cylinder waveguide. But now they are unfortunately implicit. We cannot explicitly write expressions for these things because they involve Bessel functions. This is what they look like. Dispersion relations of the first few transverse electric and transverse magnetic modes of a hollow circular cylinder waveguide. So these dispersions are a bit more complicated than those of parallel plate waveguide, and there are reasons for that. So the first feature that you can see perhaps is that transverse electric and transverse magnetic aren't identical to each other. Remember, in the case of parallel plate waveguide, they were exactly identical, well, except that transverse magnetic 0 was the odd one which existed at any frequency, and it was just identical to the light line. Here, this is not the same as this. There will be some pairs that are identical. I think that TE01 and this guy TM21, no, not this one. Not this one, sorry. This one, they are actually identical. If you overlay the two plots, you'll see that they satisfy the same dispersion. They exist on the same dispersion curve. So you see two indices here. What do they mean? The first index is M. This is the azimuthal. Interesting. What have I done? TEM. This is the azimuthal index, which describes the angular dependence of the field of the waveguide mode. And the second index is L. This is, I don't understand how it works. The second index, because if we assume certain polarization and certain azimuthal index and try to solve, let's say, this equation, then for every given beta and for every m, we're going to obtain not a single solution, but a set of solutions. And these solutions are labeled by this number. This number is called the radial index. Okay? So this is radial index 1, TE11, TE12. This is radial index 2. You see the solutions, they belong to the same polarization state, to the same azimuthal number, but different radial indices, because this solution is the lowest, this is the highest. And these two are different. This is 0, m, this is m equal 2, and so on and so forth. And for transverse magnetic, we have the same situation. We have Tm 0, 1. Then we have the next mode with the same polarization, with the same azimuthal number, but different radial index. So among all these modes, TE11 is the lowest energy mode that has the lowest cutoff, and overall it has the lowest energy for any propagation constant. But in strict contrast to parallel plate waveguides, now there is a global cutoff. Below this frequency, there is no propagation in the waveguide for any polarization state. For TE, for TM, no matter what the azimuthal index is, you cannot propagate energy along the waveguide if your frequency is below that global cutoff. This is the main difference between the parallel plate and the cylindrical waveguide. And we're going to see just in the next slides that this difference is much more fundamental than just a feature of a particular geometry. So below this frequency, below the cutoff of TE, this is ridiculous. T11, there is no propagation in the waveguide. And this is just to give you an understanding of what these modes really look like, because it's more complicated than plane waves that exist between two parallel plates. So this is the field distribution of the TE transverse electric 0, 1, 0 meaning M, and 1 meaning it's the fundamental, the lowest energy mode. Solid lines are electric fields, dashed lines are magnetic fields. And this is TM01 and TM11. So this is just mirror image of this, but now it's the magnetic field which circulates along the angular direction, and electric field is radial. This is more complicated, and this is HE11. This is actually so this is the transverse electric. I think this is transverse electric 1, 1. I would have to check that after this lecture. Perhaps I was inaccurate in labeling this. I think it's T11, but I might be wrong. I will check that. So overall, the field distributions are more complicated than the parallel plate waveguide. Now this feature with the global cutoff. In fact, this is common to any waveguides which are formed by perfect electric conductor and whose cross-section is a single finite area curve, a single curve without any disjointed areas. For such waveguides, there is always a global cutoff below which the propagation in the waveguide is not allowed for any polarization state. And by a single joint curve, I mean that the cross-section, if the x is the direction of the propagation, and if we look at the waveguide in the cross-section, I mean that its cross-section must be a single curve, okay, without any parts, just a single part, a single piece, and this piece describes the position of the perfectly conducting walls of the waveguide. And it is possible to prove this statement. Let's assume that our waveguide does not have a cutoff, and there is a certain mode that can propagate at any frequency, at arbitrarily small frequency. But now if we go to arbitrarily small frequencies, then the field distribution in the transverse plane becomes quasi-static essentially. And that means we can express electric field via the quasi-static, via the electrostatic potential. And electrostatic potential satisfies Laplace equation with boundary conditions. And because this is a single piece of conductor, the potential is the same. This is just a grounded plane. The potential must be the same on the surface of a conductor. And the only solution of this equation with this boundary condition is 0. And 0 potential means 0 electric field. So in the quasi-static limit, you are not allowed to have non-trivial solutions of the wave equation propagating in a waveguide, which is bounded by a single piece of electric conductor. So what it means is that the wavelength of the field of the waveguide mode must be finite. It cannot be infinite, because when you have infinite wavelength, you have quasi-static field distribution and 0 frequency. But when the wavelength is finite, it means that instead of Laplace equation, you need to solve full Helmholtz equation, which is retarded, where you account for the retardation. And the fields which has a finite wavelength, it becomes possible to place these fields in a space surrounded by perfect conductor. Even if it's a single piece of perfect conductor, which is described by a single loop, ds. When the field is retarded, you can squeeze that field into that space because it has a finite wavelength. And this allows you to have a non-trivial field distribution. And typically, this global cutoff wavelength is comparable to the largest transverse dimension of the waveguide. So in this case, that would be this dimension, and the cutoff frequency typically would be comparable to cutoff wavelength would be comparable to that dimension of the waveguide. For wavelength larger than that, there would be no propagation. However, this is not true when the waveguide is composed of a few pieces of conductor. Remember, our parallel plate waveguide, it has the upper mirror and the lower mirror. This is two pieces, and the potential at these two mirrors, it doesn't have to be the same. We can have zero potential at the ground plane and some positive potential at the top plane. And this allows us to find a non-trivial solution even in the quasi-static limit. And this is exactly what allows the TM0, the capacitor mode, to propagate in the parallel plate waveguide at any frequency. And another example of that is a coaxial line. You probably are familiar with this example. This is just two concentric perfect conductors, the inner conductor, the outer conductor, concentric. They are subject to different potentials on this surface and this surface. And there is a mode that propagates without any cutoff in a coaxial cable. Another famous example is the two-wire line. Just one metallic wire, another metallic wire, potential difference between them, and there is a cutoff-free propagation in such a waveguide. This is just also a waveguide, and you can think of this waveguide on the right as the limiting example, limiting case of the parallel plate waveguide. How about this? Let's consider two metallic planes. These are two. This is the representation of the parallel plate waveguide. So now let's make this plane finite, and let's keep this plane of the initial size, but let's start shrinking the top plate. Let's reduce the size. Let's just reduce the size to this, then to this, and then let's wrap it around itself. So let's make a wire out of this thing, okay? And this will be called, well, before the step, before we wrap it around, this would be called a three-plane waveguide, if I remember correctly. But now we wrap it around, and now we have one wire placed on top of a conducting surface. But now we can do the same procedure with this. We can start shrinking it, making finite, start shrinking, wrapping it around, and we'll end up with another wire. And so by doing this, I don't know if one can call it a conformal transformation. I'm not sure it's conformal because actually it is, because an infinite plane by conformal transformation can be transformed into this. So this is absolutely conformal. So by doing this, such a conformal transformation, one may convert our parallel plate waveguides into the two-wire lines. And this, I hope you recognize that this is nothing but a transmission line. So a transmission line is in fact just a waveguide. This is a waveguide formed by two wires. There's a potential difference between the two wires, and the energy, electromagnetic energy that powers your TV, your computer, your lamp in the bedroom, propagates in the space between the two wires as a waveguide mode. And when there is no load, when the switch is off, all the power is just reflected back to the grid. And it's not radiating because of the huge impedance mismatch between the free space and the impedance of the transmission line. But when you connect a load, the power now channels into the loads, into the TV, into the computer, and you consume the power from the electrical grid. So this is how we made a wonderful journey from optical waveguides that can guide optical waves to power lines, transmission lines, and we saw that they are fundamentally the same exact thing. Okay, but that was a detour about electronics and transmission lines. Last time I checked the title of our course, it was something with optical radiation. So let's get back to optical business where waves oscillate faster than 50 Hertz. So let's talk about some other waveguides that can work for confining optical radiation. And remember that there are essentially two different strategies that we can use. The first strategy was to use perfect conductors, and by using perfect conductors to completely screen, completely confine the space, just in a black box. Perfect conductors, in this case, they act much as a black box by confining radiation inside the resulting Faraday cage. And the radiation just doesn't have a possibility to go outside, to leak outside. But we can use a different strategy. We can employ instead a dielectric transparent structure, and we can try to confine the radiation in that dielectric structure below the light line. So now we are really back to where we started, with the light line and solutions below the light line, which are guided proper modes. And the easiest system where this confining of electromagnetic radiation below the light line is possible, the classical example is a dielectric slab, a dielectric field. And this is the system that we're gonna now examine. So the field in the surrounding medium, they are plane waves, and if these waves become evanescent, then radiation will be confined to the system. And now we'll consider how this becomes possible in a dielectric slab of thickness L and permittivity epsilon2 surrounded by air on both sides. Again, solution splits into two polarization states, TE, TM. For TE, electric field is strictly perpendicular to the propagation direction. We can write the fields in media 1, 2, and 3. This is 3 as a single plane wave in 1, a single plane wave in 3, which is propagating or evanescent, doesn't matter. That will be determined by K3 and K1, and the combination of two waves in medium 2 that propagates in this direction and in this direction. Okay, and the wave vectors in the environment are given by the usual dispersion relation, KZ1, KZ3. They are given by the square root K0 squared minus beta squared. Okay, but now we want the fields to be exponentially localized near the surface. So we need to require we need to impose certain requirements and limitations on these wave vectors. This field distribution describes a proper mode, exponentially localized mode, if and only if imaginary part of this guy is positive and imaginary part of this guy is negative. Only this will yield the proper mode. So we'll be looking for solutions that have those characteristics. And the wave vector inside the slab is given by this square root, and the choice of the plus or minus sign doesn't matter because we have the two plane waves at the same time. So what we do now? Well, now we need to impose the boundary conditions here and here. Electric field, tangential component of electric field and tangential component of the magnetic field are continuous. Now I'm going to skip the math and give you the dispersion equation, which is now only implicit again. Unfortunately, we have to plug KZ2, or find KZ2 from here, plug that into here, and find beta from this expression. A very, very tedious exercise, but it needs to be done. And then in a similar way, we arrive at the implicit dispersion relation of TM polarized modes, which have magnetic field perpendicular to the propagation direction. And this is the resulting dispersion plots of waveguide modes of a dielectric slab with permittivity, I think, 16. So the picture is quite simple. Dispersion curves of all the modes are sandwiched between the two light lines. The light line of the environment, air, and the light line of our dielectric, of our core waveguides. And all the waveguides, all the dispersions are going to be bounded, sandwiched between these two lines, no matter how far you go. Because the waveguide mode cannot go here, it is forbidden to go here, it's not allowed, because here the solution becomes radiating. And it also cannot go here, because here the field inside the film becomes evanescent. But the field inside the waveguide, here, it needs to remain propagating, because the field needs to carry energy in this direction. It cannot be evanescent. What else to say? You see these frequencies on the light line, which are the starting point of every pair of T and T modes. T and T modes, they start from the same points. And there is the couple of fundamental modes, the fundamental TE1 and fundamental TM1, which do not have any cutoffs, which propagate at any frequency, start at 0, and they are pretty close to the light line at low frequencies, because at these frequencies, the waveguide mode essentially becomes completely delocalized in space, and it behaves just as a plane wave, very, very, very weakly bound to the dielectric field. And lastly, we can again change the geometry. We can keep the dielectric material, but we change the geometry, and we consider a circular dielectric cylinder of radius A surrounded by air. Derivation of the dispersion relations is quite technical, so I'm gonna skip a good fraction of it. But essentially, the electric field in the dielectric material is described by a certain Bessel function. Again, non-Neumann function, because the field must remain finite at every point, so we keep on the Bessel function, which describes the radial components of the field. Okay, then we have the exponent that describes the angular behavior of the fields, and we have the propagation constant. And the dispersion relation for the radial components of the wave vector is simply this. And then the field outside the waveguide is given by the Hankel function. So what is Hankel function? Hankel function is a cylindrical function, a solution of the Bessel equation that describes an outgoing wave. So a Bessel function is basically a standing wave, a standing cylindrical wave. But outside the waveguide, the field has a different behavior. It must be an outgoing wave. And therefore, we're going to use H1, which means the Hankel function of the first kind, okay? And furthermore, if we want to obtain a proper mode, we need to require that, again, imaginary part, K rho 1 is positive, which will yield us a proper mode that will be exponentially localized near the cylinder. And then, again, by imposing boundary conditions on the surface of the cylinder, we can obtain the dispersion relations, which appear to be very, very, very complicated for the case of dielectric cylinders. Don't ask me why, but such is life. The general dispersion relation is very complicated, and one of the nasty properties of this dispersion relation is that it doesn't generally split into TE and TM polarization. It just doesn't. It only does so for M equals 0. For the monopole mode, for the azimuthal index of 0, this dispersion, because this vanishes, right? And so this becomes 0. And this splits into two sub-equations. One of them describes transverse magnetic mode, the other describes transverse electric mode. But only for the monopole mode. For the dipole and higher, it does not, and generally modes will couple, giving rise to hybrid modes that are notated EH, NM, HE, MN, and so on and so forth. This is a very complicated classification of guided modes in dielectric cylinders, unfortunately, but again, such is life. But anyway, just to give you a general understanding of waveguide modes in cylinders, I'm going to show you the dispersion diagram showing dispersion of guided modes of a dielectric cylinder with permittivity of 4. And in principle, at some level, the resultant picture is similar to what we saw with dielectric slabs, right? The dispersions again are sandwiched between the two light lines, the light line of the environment and the light line of the core of the waveguide. They cannot go here because they will be radiating, and they cannot go here either because then they will be evanescent inside the core, and that cannot happen. And then we have transverse magnetic monopole with different radial numbers, transverse electric monopole. They do have cutoffs always, and the only modes of the dielectric cylinder waveguide, circular cylinder waveguide, which doesn't have a cutoff, is the so-called HE11 or the dipole mode. The dipole mode with m equal 1 doesn't have cutoff and can propagate at any frequency. So that will be it for today, guys. Thank you for your attention. The take-home message from today's class is the basics, fundamentals of waveguiding, classification into proper and proper modes, the concept of leaky modes, waveguides with perfect electric conductors, the general properties of cutoffs, and the existence of global cutoff frequencies for single conductor waveguides, and dielectric waveguides that work using the principle of total internal reflection. That's all. Thank you for your attention, and see you next time. Bye-bye.